AWS Cloud WAN and Next-Gen Firewall Integration. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this video series, we are going to do a deep dive into AWS Cloud WAN, which is Amazon's managed wide area networking service, and then explore how to integrate next-generation firewalls, specifically Fortigate and Palo Alto networks, into that architecture for east-west and north-south traffic inspection. This is a topic that comes up constantly in enterprise cloud network design. Organizations are adopting Cloud WAN as a replacement for traditional transit gateway mesh topologies, and they need to understand how security services fit into that model. By the end of this series, you will understand the building blocks of Cloud WAN, its policy model, its routing constructs, and the two primary firewall integration patterns used in production deployments today. Cloud WAN Core Architecture Components. Let me walk through the architecture diagram for Cloud WAN's core components, because understanding the hierarchy of objects is essential before we can talk about routing or firewall integration. The global network is the outermost container. It is the logical representation of your entire enterprise network within AWS Network Manager. You create one global network per organization, and every other Cloud WAN resource lives inside it. Think of the global network as the boundary of your managed WAN domain. Inside the global network sits the core network. The core network is the operational backbone. It is what AWS actually deploys and manages for you. The core network is defined by a core network policy document, which is a JSON document describing which regions are active, how segments are defined, and what the routing behavior should be. The core network connects to a set of core network edges, which are the regional endpoints where your attachments terminate. Core network edges, also called CNS, are the regional points of presence for your core network. When you activate a region in your core network policy, AWS provisions a CNE in that region. The CNE is the regional entity that accepts attachments from VPCs, VPN connections, and transit gateway peerings. The arrow from core network to core network edge represents this containment relationship. Each edge belongs to exactly one core network. Attachments are the connection points where your workloads and connectivity resources plug into the core network. A VPC attachment connects a specific VPC to a CNE in the same region. A VPN attachment connects an on-premises site using IPsec. A Connect attachment supports SD-WAN appliances using GRE tunnels with BGP. A transit gateway peering attachment connects an existing TGW to the core network for hybrid or migration scenarios. Finally, segments are the logical routing domains within the core network. Every attachment is placed into exactly one segment, and segments control which attachments can communicate with each other through segment sharing and routing policies. Cloud WAN attachment types. Understanding attachment types is critical because the attachment type determines what connects to the core network, what BGP attributes are available, and how routing is controlled at the attachment level. Each attachment type has its own configuration characteristics and use cases. Looking at the diagram, we have the core network edge at the center, with 4 attachment types radiating from it. This star topology represents how all attachment types terminate at the regional CNE. The VPC attachment is the most common type. It connects an entire VPC to the core network by attaching to one or more subnets in that VPC. Specifically, dedicated subnets in each availability zone designated for Cloud WAN attachment ENIs. The VPC's CIDR block is then advertised into the assigned segment. You can control which subnets are reachable via the attachment using the appliance mode setting and subnet route table configurations. The VPN attachment supports site-to-site IPsec VPN connections from on-premises routers or SD-WAN edge devices. The VPN attachment uses BGP to exchange routes between the on-premises device and the core network. It supports IKEv1 and IKEv2, and you can configure static or dynamic routing. BGP attributes like AS path and MED can influence path selection in multi-VPN scenarios. The Connect attachment is designed for high-performance connectivity with SD-WAN appliances or third-party network virtual NBAs running inside AWS. Connect attachments use GRE tunnels with BGP over a parent VPC or VPN attachment. They support up to 5 gigabits per second per tunnel and are the preferred method for connecting to transit VPC appliances. The Transit Gateway peering attachment connects an existing AWS Transit Gateway to the core network. This is critical for migration scenarios. Organizations that have already built complex TGW architectures can peer their TGW to Cloud WAN, selectively migrating segments over time rather than performing a hard cutover. Routes are exchanged via static configuration across the peering attachment. Security Integration Architecture Overview. Now that we understand the Cloud WAN building blocks, let's talk about how next-generation firewalls integrate into this architecture. There are two primary design patterns used in production environments, and they both rely on a dedicated inspection VPC connected to the core network as a specialized segment. Looking at the diagram, the overall model shows spoke VPC's production and development workloads connected to the core network via VPC attachments. These spokes are in their respective segments. Traffic that needs to flow between segments, or traffic leaving to the internet, must be steered through an inspection segment that hosts the firewall appliances. The send via routing action in the core network policy is the mechanism that forces inter-segment traffic through the inspection segment. When you configure a send via action, you designate the inspection segment as the via segment. Cloud WAN then programs routes in the core network so that traffic from the production segment destined for the development segment, or vice versa, is hairpinned through the inspection segment before being forwarded to the destination. Inside the inspection VPC, the firewall appliances sit between a pair of gateway load balancer endpoints. Gateway Load Balancer, or GWLB, is the AWS service used to transparently redirect traffic flows to third-party virtual appliances. GWLB uses the Geneve protocol on port 6081 to encapsulate traffic and pass it to appliance instances in a target group. The appliances inspect the traffic, apply policy, and return it to GWLB, which then forwards it to the original destination, all transparently, without changing source or destination IP addresses. This is important. The firewall sees the original source and destination IPs of the workload traffic, not tunnel endpoints, which allows security policy to be written against real workload CIDR blocks. Fortigate and Palo Alto both support GWLB integration natively through their respective Geneve decapsulation capabilities. Fortigate integration with AWS Cloud WAN. Fortigate is Fortinet's next-generation firewall platform, available in AWS as the Fortigate VM, which runs FortiOS. Fortinet has native AWS integration including Gateway Load Balancer support, AWS SDN connector for dynamic address objects, and CloudFormation templates for deployment. Let me walk through how Fortigate integrates with Cloud WAN specifically. Looking at the diagram, the Fortigate integration follows the inspection VPC pattern we described, with some FortiOS-specific configuration elements. Traffic enters the inspection VPC from the core network attachment, hits the GWLB endpoint in the attachment subnet, is forwarded to the GWLB in the GWLB subnet, which distributes it to Fortigate instances in the appliance subnet. On the Fortigate instance, GWLB integration requires a Geneve tunnel interface. In FortiOS, you create a Geneve interface bound to the physical data interface. The Geneve interface has no IP address assigned. It operates in Layer 2 bridge mode, with the Fortigate effectively acting as a bump in the wire. The FortiOS policy is applied to traffic traversing from the Geneve interface back to the Geneve interface, with source and destination address objects matching actual workload CIDRs from the spoke VPCs. A critical FortiOS configuration element for GWLB integration is the symmetric routing setting. Because GWLB operates at layer 3 and forwards traffic based on its own routing decisions, FortiOS must be configured to handle traffic where the source and destination may arrive and depart on the same interface. The command set asymmetric route enable is required in the relevant VDOM's router settings to prevent FortiOS from dropping these otherwise valid flows. The Fortigate Autoscale group can be deployed using Fortinet's published AWS Autoscale solution, which uses a Lambda-based orchestration engine to manage license assignment, GWLB target group registration, and configuration synchronization across Fortigate instances as the group scales in and out. The primary and secondary Fortigate instances synchronize session tables via HA session sync over a dedicated sync interface or over the management subnet, ensuring that if an instance is replaced, in-flight sessions are preserved. Palo Alto Virtual Machine Series integration with AWS Cloud WAN. Palo Alto Network's Virtual Machine Series is the virtualized form factor of the PANOS next-generation firewall platform. In AWS, Virtual Machine Series instances are deployed from the AWS Marketplace and support integration with Gateway Load Balancer through a feature called GWLB Mode, which was introduced in PANOS 10.1. Let me walk through how Virtual Machine Series integrates with Cloud WAN. The VM Series GWLB integration works similarly to Fortigate at the network level. GWLB distributes Geneve encapsulated traffic to registered VM series instances. But the PANOS configuration model differs from FortiOS in how the Geneve interface is handled. In PAN operating system, Gateway Load Balancer integration is configured through a dedicated Gateway Load Balancer inspection interface type. When you select the Gateway Load Balancer integration mode during initial bootstrapping, PAN operating system automatically creates the required generic routing encapsulation endpoint, configures the loopback-based health check listener on port 80 used by Gateway Load Balancer to verify appliance availability, and sets up the interface for inline inspection. The data plane interface receives generic routing encapsulation traffic on UDP port 6081. PAN operating system decapsulates the inner IP packet, applies application ID, user ID, content ID, and security policy, then re-encapsulates and returns to Gateway Load Balancer. Panorama, Palo Alto's centralized management platform, plays an important role in Cloud WAN deployments. A Virtual Machine Series Autoscale group is managed through Panorama using the AWS plugin for Panorama, which monitors auto-scaling group lifecycle hooks and automatically registers new Virtual Machine Series instances to Panorama device groups, pushes configuration, and deregisters instances that are terminated. This ensures consistent policy across all instances in the GWLB target group. The Virtual Machine Series supports bootstrapping via an S3 bucket, which contains the init configuration.txt file specifying Panorama connectivity parameters and the bootstrap.xml with initial configuration. This S3 bootstrap package is referenced in the EC2 launch template used by the auto-scaling group, enabling fully automated instance provisioning without manual console access. Fortigate GWLB configuration. FortiOS CLI deep dive. In this slide we go into the actual FortiOS CLI configuration required to integrate a Fortigate virtual machine with AWS Gateway Load Balancer inside the inspection VPC. Every command shown here is required for a working deployment, and understanding what each one does is important for both initial build and ongoing troubleshooting. The first block creates the Geneve interface. The command config system Geneve opens the Geneve interface configuration context. The edit GWLB Geneve command creates a new Geneve interface named GWLB Geneve. You can name it anything meaningful. The set interface port 1 command binds this Geneve logical interface to port 1, which is the physical data plane interface of the Fortigate virtual machine in AWS. The set type PPP line sets the encapsulation type, which must match the Geneve specification used by AWS Gateway Load Balancer. The set remote IP command sets the Geneve tunnel remote endpoint. This must be the IP address of the Gateway Load Balancer endpoint in the same availability zone as the Fortigate instance. AWS assigns this IP automatically when you create the Gateway Load Balancer endpoint service, and you retrieve it from the VPC Endpoints console or via the AWS command line interface. The end command saves and exits. The second block configures the system interface settings for port 1. The set allow access ping line enables ICMP on the physical interface so GWLB health checks succeed. GWLB uses TCP port 80 health checks by default, but ICMP is needed for connectivity validation. The set role LAN designates port 1 as a LAN-facing interface within FortiOS, which affects implicit policies. The third block is the firewall policy. The source interface Gateway Load Balancer Geneve and destination interface Gateway Load Balancer Geneve settings are both pointing at the same Geneve interface. This is correct and intentional. For Gateway Load Balancer inspection, traffic arrives on the Geneve tunnel and after policy evaluation must be returned on the same Geneve tunnel. Setting the action to accept with UTM status enable activates security profiles. The AV profile, IPS sensor, and web filter profile lines attach the respective security profile objects to this policy. The log traffic all line enables full session logging to FortiAnalyzer or a syslog target. Palo Alto Virtual Machine Series Bootstrap Configuration. Palo Alto Virtual Machine Series instances in an auto-scale group must be bootstrapped automatically without any manual console interaction. The bootstrap mechanism uses an S3 bucket with a specific directory structure that PAN-OS reads during first boot via the EC2 instance's user data or metadata service. Getting the bootstrap package right is essential because any misconfiguration means the instance fails to register with Panorama and is never added to the GWLB target group. The S3 bucket structure has 4 directories under a configurable prefix. The config directory contains the bootstrap.xml file, which holds the initial device configuration including hostname, DNS settings, and the initial admin credentials. The license directory contains the authorization code or the license file for the Virtual Machine Series license bundle you purchased. The software directory can contain PAN operating system software images for an automatic update on first boot. The content directory can contain content updates including application ID signatures, threat prevention signatures, and URL category databases. The initcfg.txt file is placed directly in the root of the bootstrap prefix, not inside a subdirectory. This is a common mistake. The initcfg.txt uses a key equals value format. The Panorama server key specifies the primary Panorama IP or host name. The Panorama server 2 key specifies the secondary Panorama for high availability. The TPL name key specifies the Panorama template stack name to apply to this device. The DG name key specifies the Panorama device group. The VM auth key is a pre-shared key generated on Panorama that the VM series uses to authenticate its registration request, preventing unauthorized devices from self-registering. The EC2 launch template for the auto-scale group references the S3 bucket in the user data field using a key value format that PAN-OS parses during boot. You also need an IAM instance profile attached to the launch template that grants the EC2 instance get object and list bucket permissions on the S3 bootstrap bucket. Without this IAM permission, the instance cannot read the bootstrap files and boots with a blank configuration. Route table design inside the inspection VPC. The internal routing of the inspection VPC is one of the most nuanced aspects of this entire architecture, and incorrect route table configuration is the most common cause of traffic blackholing in Cloud WAN firewall insertion deployments. Let me walk through each subnet tier's route table requirements. The Cloud WAN attachment subnet route table has the simplest requirements. It needs a default route pointing to the GWLB endpoint in the same availability zone. This directs all traffic arriving from the core network toward the GWLB for inspection. AWS creates GWLB endpoint IDs in each AZ. These are VPC endpoint resources of type Gateway Load Balancer, and each one gets a private IP in the GWLB subnet. The route table entry uses the GWLB endpoint ID as the target, not an IP address. There should be no route back to the core network in this route table. That return path is handled automatically by the GWLB and the core network attachment after inspection. The GWLB subnet route table needs a route back to the Cloud WAN attachment for traffic that has completed inspection and needs to be forwarded. The GWLB itself sends post-inspection traffic to the GWLB endpoint, which then needs a path to the destination. The route table for the GWLB subnet typically carries a default route pointing to the core network attachment ENI for traffic heading back into the WAN fabric. For any traffic destined to the Internet centralized egress scenarios, there would also be a route to the NAT gateway or Internet gateway depending on the design. The appliance subnet route table is the most complex. The firewall instances need reachability to the Internet for license activation and signature updates. This is done via a NAT gateway in a management subnet, not through the GWLB path. The appliance subnet also needs routes to any out-of-band management resources like the FortiManager or Panorama management IPs. A separate management interface on the Fortigate or VM series instance handles this traffic, and the management subnet has its own route table with a NAT gateway route for Internet-bound management traffic. Multi-region Cloud WAN design. One of the primary use cases for AWS Cloud Wide Area Network over Transit Gateway is its native multi-region capability. Adding a new region to an existing Cloud Wide Area Network deployment requires only a policy update, no manual peering, no route table modifications across multiple regions. Let me walk through the multi-region architecture and what AWS actually provisions behind the scenes. In the diagram, we have three active regions: US East 1, EU West 1, and Asia Pacific Southeast 1. Each region has its own core network edge, and AWS maintains fully meshed internal BGP peering between all three CNS. This mesh is managed by AWS. You do not configure it, peer it, or maintain it. The underlying transport is the AWS Global Backbone, which provides low latency, high bandwidth inter-region connectivity. Each region has its own set of segment attachments. The production segment exists in all three regions, and production VPC routes from each region are visible to production VPCs in all other regions, subject to the routing policies you define. If you want to restrict production VPC in US East 1 from reaching production VPCs in EU West 1, you use segment isolation or service insertion to control that flow. The inspection segment also needs to be deployed in every region where you want east-west traffic inspection. A single centralized inspection VPC in US East 1 would force all intersegment traffic, even EU West 1 to Asia Pacific Southeast 1 flows, through US East 1 for inspection, adding significant latency. The recommended pattern is to deploy an inspection VPC with a firewall cluster in each active region, with the send via policy referencing the local inspection segment. This ensures traffic is inspected in the same region where the source and destination workloads reside. The core network policy edge locations array controls which regions have active CNS. Adding a new region is as simple as adding it to the array, creating a new core network policy version, and applying it. Cloud WAN provisions the new CNE within minutes, and any VPC attachments created in that region automatically inherit the segment routing policies defined globally. East-West versus North-South traffic flows. Understanding the distinction between East-West and North-South traffic flows and how each type traverses the Cloud WAN and firewall architecture is fundamental to designing both the routing policy and the firewall security policy correctly. These two traffic types require different send via configurations and may require different firewall policy zones. East-west traffic refers to lateral traffic between workloads within the cloud environment. In a cloud WAN context, east-west traffic is typically traffic between spoke VPCs in different segments. For example, an application tier in the production segment communicating with a database service in a shared services segment, or production VPCs communicating with development VPCs during testing. This traffic never leaves AWS. It travels entirely across the core network backbone and through the inspection VPC. Looking at the east-west flow in the diagram, a client workload in production VPC sends a request to a server in shared services VPC. The packet leaves the production VPC via the Cloud WAN attachment ENI, enters the core network on the production segment. The send via policy redirects it to the inspection segment. The GWLB receives it in the inspection VPC. The firewall inspects it and applies policy. GWLB forwards the inspected packet back to the core network. The core network delivers it to the shared services segment. And finally it reaches the destination server in shared services VPC. The return path is symmetric. North-south traffic refers to traffic crossing the boundary between the cloud environment and the internet or on-premises networks. North-south outbound is workload traffic leaving AWS to reach internet destinations. North-south inbound is traffic from the internet or on-premises entering spoke VPCs. This traffic uses the centralized egress pattern for outbound or a dedicated ingress path using application load balancers or network load balancers in the egress VPC for inbound. The firewall security policy must account for both flow types. For east-west, policies are written based on source and destination segment CIDRs. The firewall sees the private IP addresses of the workloads on both sides. For north-south outbound, policies match the source as internal CIDRs and the destination as quad 0/0 with URL category and application filters applied. TLS inspection is strongly recommended for north-south outbound to enable effective URL filtering on HTTPS traffic, which represents the majority of internet-bound traffic in modern environments. High availability and scaling for next-generation firewall in Cloud WAN. High availability and auto-scaling for the firewall cluster in the inspection VPC are non-negotiable requirements in a production Cloud WAN deployment. The firewall cluster sits in the critical path for all inspected traffic. Any availability issue directly impacts workload connectivity. Let me walk through the HA model, the scaling triggers, and the key configuration parameters for both Fortigate and Palo Alto deployments. Gateway Load Balancer provides the native layer of high availability for the firewall cluster. Because Gateway Load Balancer distributes flows across all healthy registered targets, the failure of a single firewall instance only affects the flows that were pinned to that instance. Gateway Load Balancer detects unhealthy targets within its health check interval defaulting to 30 seconds with a threshold of 3 consecutive failures and removes them from the distribution set. New flows are distributed only across healthy instances. Existing flows that were pinned to the failed instance are interrupted, but TCP-based applications will retransmit and establish new connections that are distributed to healthy instances. The auto-scaling group manages horizontal scaling. The primary scaling metric for firewall clusters is CPU utilization of the firewall instances, typically measured via CloudWatch. A target tracking policy set at 70% CPU triggers scale out, adding new instances to the target group. Network throughput metrics from GWLB, specifically the processed bytes per target, can be used as a secondary scaling metric if the firewall is I/O bound rather than compute bound. For Fortigate, the Fortinet Autoscale solution uses a primary and secondary Fortigate design within the cluster. The primary Fortigate handles license management and configuration distribution to new instances joining the Autoscale group. New Fortigate instances bootstrap by contacting the primary instance rather than FortiManager directly, reducing the dependency on external management infrastructure during scale-out events. This architecture works because Forti operating system supports a cloud-native HA mode called FGCP on AWS that is distinct from traditional FGCP active-passive HA used in on-premises deployments. For Palo Alto, the Panorama AWS plugin handles all scaling lifecycle events as we covered earlier, and there is no concept of a primary instance within the cluster. Each VM-series instance is fully independent and receives its complete configuration from Panorama. This means Panorama must be reachable from new instances at all times during scale-out. A dedicated Panorama Management VPC connected to the core network with appropriate routing ensures management plane reachability across all regions. Fortigate SD-WAN and Cloud WAN Connect attachments. Fortigate's SD-WAN engine and AWS Cloud WAN Connect attachments are a powerful combination for organizations that need intelligent path selection and application-aware routing between branch sites and AWS workloads. This slide covers how these two technologies integrate at both the data plane and control plane level. A Cloud WAN Connect attachment is designed specifically for high-performance third-party appliance connectivity. Unlike a VPN attachment which terminates IPsec tunnels, a Connect attachment establishes GRE tunnels with BGP running inside them. The GRE tunnel originates from a network virtual appliance, in this case Fortigate, running inside a transit VPC or directly inside a spoke VPC. The Connect attachment requires a parent attachment, either a VPC attachment in the same VPC or a direct Connect gateway attachment, and builds the GRE tunnel over that parent. On the Fortigate side, the SD-WAN configuration defines multiple WAN underlay links. These could be AWS Direct Connect, site-to-site VPN over the Internet, or the GRE-based Connect attachment tunnel itself. Fortio's SD-WAN health checks continuously measure latency, jitter, and packet loss on each underlay link. SD-WAN rules then match traffic by application signature or DSCP marking and select the best performing underlay link for each application class. Voice and video traffic with real-time requirements get routed over the lowest latency path, while bulk data transfers use the highest bandwidth available path. BGP is used to exchange routes between Fortigate and the Cloud WAN core network edge over the Connect attachment tunnel. The Connect attachment supports BGP ASNs in the private range and allows advertisement of on-premises prefixes learned from branch-side BGP sessions directly into the Cloud WAN routing fabric. This makes Fortigate a route reflector between the SD-WAN fabric and the Cloud WAN global backbone, enabling fully dynamic route propagation from branch to cloud workload without any static route configuration. Cloud WAN network policies, traffic engineering. Beyond segment routing, AWS Cloud WAN supports a set of network policy constructs that give engineers granular control over how traffic is forwarded across the core network backbone. These constructs allow you to influence path selection, enforce bandwidth constraints, and apply DSCP markings as traffic enters and exits the core network. The first construct is the via segment routing policy, which we have already covered in the context of firewall insertion. However, it is worth noting that via segment can also be used for pure traffic engineering purposes, forcing specific attachment to attachment flows through a transit processing point without a firewall, such as a packet broker, a network performance appliance, or a data loss prevention proxy. The second construct is the service insertion network function. This is a newer Cloud WAN capability that natively models third-party appliances as network functions within the policy. Rather than manually configuring GWLB and routing tables, you declare the network function in the core network policy and Cloud WAN automates the traffic steering. Fortigate and Palo Alto are both listed as supported network function types in the AWS Marketplace integration for this feature. Looking at the diagram, the traffic engineering policy shows how DSCP markings can be used to influence path selection across the backbone. Traffic from production VPCs tagged with DSCPEF, expedited forwarding, is assigned to a low-latency backbone path. Traffic tagged with DSCPAF11, assured forwarding, is assigned to a standard path. The Cloud WAN backbone uses these markings to differentiate traffic classes. DSCP markings must be set by the workload or the firewall inspection policy before the traffic enters the Cloud WAN attachment, as Cloud WAN itself does not perform DSCP remarking on ingress. Transit Gateway Migration Strategy to Cloud WAN. Most organizations adopting Cloud WAN are not starting from a greenfield environment. They have existing transit gateway architectures with mature route table configurations, VPN attachments, and direct connect gateway associations. AWS provides a supported migration path using Transit Gateway Cloud WAN peering, which allows incremental migration without any production traffic disruption. The migration follows a phased approach. In Phase 1, a new cloud-wide area network core network is created alongside the existing transit gateway infrastructure. No workloads are moved yet. The core network policy is designed to match the final target architecture. Segments are defined, send via policies are configured, and the inspection VPC with firewall cluster is deployed and tested in isolation. This phase validates that the new architecture functions correctly before any production traffic touches it. In Phase 2, a transit gateway peering attachment is created between the existing TGW and the new core network. Static routes are configured on the peering to selectively advertise specific spoke VPC CIDR ranges from the TGW into the Cloud WAN core network. On the TGW side, a new route table association is created for a test spoke VPC, pointing its traffic toward the peering attachment. This allows a single spoke VPC to be migrated to Cloud WAN routing while all other VPCs continue using the original TGW route tables. Traffic between the migrated spoke and remaining TGW attached VPCs traverses the peering attachment during the migration window. In Phase 3, spoke VPCs are migrated in batches. Each spoke VPC migration involves detaching from the TGW and creating a new VPC attachment to the Cloud WAN core network in the appropriate segment. The attachment policies in the core network policy automatically assign the VPC to the correct segment based on environment tags. After each batch migration, validation confirms reachability to on-premises, to other spoke VPCs, and to shared services. Phase 3 continues until all spoke VPCs are migrated. Phase 4 decommissions the transit gateway. VPN and Direct Connect gateway attachments are moved from the TGW to Cloud WAN VPN and Connect attachments. The TGW peering attachment is removed. The TGW itself is deleted after confirming zero traffic for at least 24 hours. At this point, the architecture is fully on Cloud WAN with no TGW dependency. TLS inspection. Fortigate and Palo Alto approaches. TLS inspection, also called Secure Sockets Layer Deep Inspection or HTTPS inspection, is the process of decrypting encrypted traffic at the firewall, inspecting the decrypted content, and re-encrypting before forwarding. Without TLS inspection, a significant portion of threats and policy violations are invisible to the firewall because they are hidden inside HTTPS, SMTPS, or other TLS encrypted protocols. In modern cloud environments where well over 90% of web traffic is HTTPS, TLS inspection is effectively a requirement for meaningful threat prevention. In the Cloud WAN architecture, TLS inspection is performed inside the inspection VPC by the firewall cluster. Traffic arrives at the firewall via GWLB already decapsulated from Geneve. The firewall sees the original TLS encrypted payload with the original source and destination IP addresses. The firewall then acts as a man in the middle. It terminates the client's TLS session, decrypts the content, applies security inspection, and establishes a new TLS session to the server using the firewall's own certificate. The client receives a dynamically generated certificate signed by the firewall's CA certificate rather than the server's real certificate. For TLS inspection to work transparently, The firewall CA certificate must be trusted by all clients. In a corporate environment, this is done by distributing the firewall CA certificate via group policy or an MDM solution to all managed endpoints. AWS workloads running as EC2 instances or containers must have the certificate added to the operating system's trust store or the application's certificate bundle. This is typically handled via user data scripts or configuration management tools like Ansible or SSM State Manager. Fortigate implements TLS inspection through an secure sockets layer/SSH inspection profile attached to the firewall policy. The profile specifies which certificate to use as the signing CA, which TLS protocol versions are permitted, and which cipher suites are allowed. FortiOS can perform full inspection or certificate-only inspection. The latter verifies the server certificate without decrypting payload, useful for banking and healthcare sites where regulatory or compliance concerns require traffic to remain encrypted end-to-end. And secure sockets layer exemption list allows specific domains or categories to bypass inspection. Palo Alto Networks implements TLS inspection through decryption profiles and decryption rules in PAN-OS. A decryption rule specifies the source zone, destination zone, application, URL category, and the decryption profile to apply. The decryption profile controls TLS version constraints, certificate verification behavior, and session limits. PAN-OS supports hardware-accelerated decryption on physical appliances and software-accelerated decryption on virtual machine series, which is important for throughput planning in high-traffic Cloud WAN inspection scenarios. End-to-end reference architecture. This slide brings together every component we have covered throughout this series into a single comprehensive reference architecture diagram. This is the production-ready design that organizations can use as a starting point for their Cloud WAN and NGFW deployment. Let me walk through every element of this architecture from the on-premises edge all the way to the cloud workload tier. Starting with on-premises connectivity. Branch sites connect through Prisma SD-WAN on devices or Fortigate SD-WAN appliances over dual WAN links, one direct connect and one internet-based backup to the Cloud WAN core network via connect attachments terminating in a transit VPC. The transit VPC is attached to the core network in its own segment, called the SD-WAN segment, which prevents branch traffic from directly reaching production VPCs without traversing the inspection segment. The core network spans 3 regions, US East 1 as the primary region, EU West 1 as the EMEA region, and Asia Pacific Southeast 1 as the APAC region. Each region has its own core network edge. The AWS managed internal BGP mesh between CNS propagates segment routes globally. Each region has its own inspection VPC with a GWLB-fronted firewall cluster-Fortigate or VM-series depending on the organization's platform choice deployed in an auto-scaling group managed by FortiManager or Panorama respectively. The segment structure is consistent across all regions. The production segment contains production spoke VPCs. The development segment contains development and test VPCs. The shared services segment contains DNS, Active Directory, and patch management VPCs. The SD-WAN segment contains the transit VPC that terminates branch connectivity. The inspection segment contains the inspection VPC with the firewall cluster. The egress segment contains the egress VPC with NAT gateways for centralized internet egress. The send via routing actions in the core network policy enforce that all inter-segment traffic passes through the inspection segment before reaching its destination. All traffic from any segment destined for the egress segment also passes through the inspection segment for outbound URL filtering and TLS inspection. This means every east, west, and north-south flow in the entire global network is inspected by the firewall cluster in the local region, with no traffic bypassing the inspection path regardless of source or destination segment. Series summary and key takeaways. We have covered an enormous amount of ground across this video series, And I want to take the final slide to summarize the key design principles that should guide any AWS Cloud WAN and next-generation firewall deployment. The first principle is segment-first design. Before writing a single line of core network policy JSON, define your segments based on your security zones, not your VPC structure. The segment is the routing domain, and everything flows from how you define segments and their sharing relationships. A well-designed segment structure makes routing policy simple. A poorly designed one creates compensating complexity that is hard to maintain. The second principle is local inspection. Deploy an inspection VPC with a firewall cluster in every active region. Centralizing inspection in a single region creates a hub-and-spoke traffic pattern that reintroduces the latency and capacity constraints that Cloud WAN was designed to eliminate. Local inspection keeps traffic inspection within the same AWS region as the workloads, minimizing latency impact. The third principle is automation over manual configuration. Both Fortigate and Palo Alto provide automation frameworks, Fortinet Autoscale and Panorama AWS plugin that handle the full lifecycle of firewall instances in auto-scaling groups. Do not attempt to manually manage firewall instances in a GWLB target group. The automation handles health, policy consistency, and scaling in ways that manual processes cannot match at cloud scale. The fourth principle is observable by design. Enable CloudWatch metrics on all Cloud WAN attachments, VPC flow logs on all inspection VPC subnets, and firewall logging to a centralized log management platform from day one. Trying to add observability after a production incident is far more difficult and time-consuming than building it in from the start. The ROT analyzer in Network Manager should be part of every troubleshooting runbook for connectivity issues. Thank you for your attendance. Please consider subscribing to the channel and liking this video.